As for the others, I want to thank the organizers for setting up this conference. It's been very nice, and the city is really nice as well, so I'm really enjoying my time here. So the work I'm presenting today is a joint work with Eric, who's somewhere in the room over there. And I have to give him credit for the nice math. He's the one behind that. I'm just waving hands around. So the idea of what we want to do is we want to work with the Tobin model. If anyone has done some work on SFC, quickly you've seen that this is where most of the fun happens in the financial sector, and that's where most of this instability emerges, and so you quickly become very frustrated with the way it's been set up. Of course, as a Keynesian, well, you think uncertainty is important, and so you want to account for uncertainty and risk. And so, again, you quickly become frustrated with the way the Tobin equation are working. So, well, when Eric proposed this work, I was like, yay! I'm going to put my hands in there, it's going to be brilliant. But brilliant, I don't know. We'll let you judge after that. Well, meet the Tobin model. So the Tobin model is a model which allocates different types of wealth, wealth into different types of assets. And theoretically, you could have as many as you want. If you look at the data, often you have bonds, equity, bills, maybe deposits, SDRs, well, a few of assets, but in practice, it could be actually extended to many more assets. And it has been actually picked up by development economics as well, quite a lot. And so they've been doing flow of fund models, trying to estimate how Indian households allocate their wealth into different assets they can buy. The empirics of it are difficult, as Steve was mentioning the other day. Yes, well, today actually, not the other day. If you try to estimate that directly using level data, it doesn't work, because there's lots of trends, and you want to explain, okay, how do the trends come here, and it can't be only explained by the return rates. So again, you need to, that justifies again why we want to work more. So how does it work? The idea is that here the S would be the share of wealth, so of total wealth allocated to a type of asset. So we just divide the market value of an asset by the total wealth of the portfolio. So these are the shares. And then the idea is that the shares are the result of an allocation between what we call the base share, the lambda I zeros, and I'll come back to that in a minute, mitigated by the relative returns of the different type of assets. So if one asset has a high return, then it's likely that the base share will increment, the share will be higher than the base share. And the base share can be interpreted as what would be the allocation if all the returns were equal. Assuming we live in Modigliani-Miller world, then all the returns are equal, and so only the base share would explain how you would distribute your wealth. Right. There's been a bunch of constraints. Of course, you have that the base share have to satisfy the sum to 0, otherwise they wouldn't be shares. No, sum up to 1. Sorry, that's a lambda I0 should be sum to 1, sorry, otherwise they wouldn't be shared, there it is. And then there's a few other equations where the lambda ij have to sum up to 0 if you sum them over a row. And the idea is that you can gain as much as by increasing your return, the own return rate of an asset, as by having the other return rates decrease. So it should be symmetrical in that aspect. And often you actually can add that to a symmetrical condition where you just basically assume that the lambda ij is equal to lambda ji. But that's not necessary. That's something we add often, but that doesn't have to be the case. Right, so now let me just add a few more equation notation. The first one is we can then, from the model that Tobin developed, go back to Tobin's Q, where we define Tobin's Q as the share assigned to the assets multiplied by the wealth divided by the capital value. You could theoretically remove lendings here, but let's just abstract from lending. So basically what we assume is that what we show is that we can compute Tobin's Q by just looking at the share of the portfolio, coming out of the portfolio multiplied by the wealth divided by the capital stock of the type, the specific sector or asset. And then you can, if we accept that, well, if we show that the average Tobin skew is equal to the total wealth minus what you store as money in the economy, so total wealth minus money divided by k, that's the average Q in the economy. Then you can write down that the share of a specific asset is equal to, we can basically rewrite it and show that the share is basically a proportion of Tobin's Q over the average Q. Am I making any sense? Right? Okay, good. And then what we show here is that the money being the last asset in the portfolio, the share of money is equal to the money holding. And if the Tobin skew is equal to 1, which was the assumption that Tobin was having, so he was saying that in the long run, there would be no reason why the Tobin skew wouldn't be equal to 1. So if the Tobin skew is equal to 1, then in that specific case, we call the share Wi. So the two of them represent the same idea, but Wi is a specific case when Tobin skew is equal to 1. And in that case, Tobin's Q is equal to 1, the average Q is equal to 1, so this simplifies, and the weight share, the share is this one here. And M star would be the money holding when the total Tobin's Q are equal to 1. Right, so how do we start? We say, okay, well, let's start with indistinguishable assets, meaning that they all have the same risk, and then we'll see how, when we introduce risk, this can change. So we start with the model with same risk, but randomly they have different return. How would the model then change? Well, ideally all wealth would be moved to the highest return bearing asset. Of course, this is self-defeating because as you invest more into that asset, the return decreases, and so you have this equilibrium, and so basically you move and up to the point where all the returns tend to equilibrium. So in a case where all the risks are the same, there's nothing that would prevent the model to have all the returns being equalized by just having buy and hold strategies. Now, so at equilibrium, all the returns are equalized and Tobin's Q are equal to 1, and so we just have the lambda I0 equal to Wi, which is the share when Tobin's Q are equal to 1. What happens if one asset has an increase in returns, delta Rj? Of course, as we explained before, we cannot have all the wealth moving to that asset, otherwise it would be self-defeating and then we would equalize again. So it is important to understand how much is this asset going to absorb the existing wealth, and that's why we call this absorptive capacity of the asset J. And what we propose, and this is just the assumption we're making, is that it has to depend on how much it will impact from the current share of wealth. So the more you absorb, the more the higher the lambda ij will be, and this A term here is this absorptive capacity. And you see that the lambda aj satisfy the constraint condition, so that they sum up to 0, they're symmetrical and so on. So this proposed notation actually works quite well. But here we're still without a risk. So what happens when we increase risk? And the risk, what it will happen is that the risk can be measured, the introduction of risk can be, and the impact of the introduction of risk can be measured by the tendency for the returns to defer. Sorry, I'm jumping ahead. What is risk first? And the definition we accept to take here is that it's the tendency for returns to differ from an expectation. I.e., if there's a lot of volatility, for example, then returns are changing a lot, this is perceived as risky. Whether, and so the difference from expectation can be either from looking at a historical mean or for a particular asset or return for a benchmark asset, like using the CAPM or whatever. We don't have a specific definition. We are happy with this definition, which is broad enough. And we can have a definition which is valid for a specific asset, an absolute measure, or compared to a benchmark, a relative measure. There's lots of indicators about risk. This literature is there. Actually, professional investors usually tend to say, well, academics are completely wrong about it, so you should not look at the indicators and we'll pick a better indicator. We had to make a choice, and so we follow the conventional academic notation, and we assume that we can set a risk VI, which is independent of the other assets. So each VI is independent of the other risk, and it's computed for that type of asset. And also, we assume that there is no relationship between risk and return, which is something which actually empirically has been shown. In the model, we assume that, but the correlation actually, again, empirically, we have seen that the correlation can be either positive, negative, zero, depending on the measure and depending on the data set and so on. So we just say, we start with the assumption that there's no relationship between risk and return. So to add up the risk in the story, what we say is that no, the market is going to be characterized by two parameters. The first one is a tolerance for risk, a targeted risk level in the portfolio, and then a preference for keeping turnover low, meaning that you don't want to, as soon as risk change, you don't want to change too fast your portfolio. And the reason being is that you have fees for brokering, you might have imperfect information, what have you. So even though the risk level or the tolerance for risk might change, it might take some time before the whole system adapts. And what we do is then we assume that there's a maximization process between the sum of the average returns, which you want to, of course, have highest as possible, and the deviation from the equilibrium share WI, and that's captured by the idea of keeping the turnover low. So you don't want to deviate too much from the equilibrium share. And of course, we are subject to a constraint that enforces the risk tolerance. You don't want to go above the targeted risk. So we need to find a definition of how do we deviate from the weights. And what we assume is we use this deviation function, which is of this form. So the deviation function is depending on how far the current share allocation is different from the equilibrium share allocation. And we don't specify the function, but we'll show you in a minute how we can nonetheless get an approximation of that by just using a Taylor rule expansion. Right, yeah. So, as I said, we can approximate the deviation function by using the Taylor approximation. We can show it's in the paper that it's basically the second term, which is non-zero, and second order. And so this is the deviation function we use, where R star is a parameter we use for to keep the unit correct. And so we feed then this deviation function into the objective function. So this is the term which says we want to maximize the returns, where SI is the allocation of each asset and RI is the return on each asset. And then this is, there's a minus sign here, so you want to minimize the deviation from the optimum distribution. And then we enforce that the risk tolerance is respected, that the shares are actually shares, and that they're all positive. When you put all this together, you get the Lagrangian, which is here. I won't go too much into that. The only thing that maybe was worth mentioning is that this term here is a trick where we show that this is the positivity constraints, where we basically show that SI has to be equal to AI squared, i.e. has to be a positive number. The first order condition of the Lagrangian gives us these two constraints, aside from the obvious risk tolerance constraint and the sum to 1. And we have two cases, either theta I is equal to 0, AI is equal to 0, but if theta I is equal to 0, then it's a not very interesting case, so we consider only in the case where AI is equal to 0. If we put AI equal to 0 into here, then we can get an expression for the shares. And so the share, then we have basically, out of this maximization problem, we basically said that the share of wealth allocated to an asset depends on its equilibrium share, and then a term which depends on how much the investor look at deviation from risk, deviation from equilibrium, and then the risk term, which is VI here. And so when we use this, and on top of it, the two constraints of shares equal to 1, and the portfolio is built with a specific average risk, then we can get an equation for SI, and this SI basically shows, it can be reorganized, and here what you have is the lambda I0, which we're looking for, and then terms which depends on the return, and that's the lambda IJs. So we use the notation here to express weighted sum, and A is equal to this term which depends on how much you're willing to change your portfolio. And so we have the formulation here from lambda I0 and lambda Ij's, and they respect the various constraints. And on top of that, when risk tend to a unique value, then the lambda I0s tend to WI, which is the one we had in the beginning, and that the lambda Ij tend to the equation we had written in the first place when we had indistinguishable assets. So we're quite happy about it. Now, I've bored you for what, 10 minutes, 15 minutes now about maths? Why is it interesting? I mean, in fairness, it's cool, it's nice math, and okay, but why are we doing this? Well, the first thing is that we can actually look at expression for Tobin's Q for each the assets, depending on the risk and on the different returns for all the different assets. And then we can actually use it for more interesting stuff, such as the macroprudential policies and what is the impact of a change in the capital adequacy ratio, or any of the different ratios that a macroprudential policy can use. What is the impact of, I have 3 minutes left. Okay, perfect. What is the impact of QE or green QE, and then of course doing empirics. The last two we didn't do yet, but these two ones we did. The Tobin's Q, what we can show is that the Tobin's Q then basically depends, I'm going to hear, the Tobin's Q depends on the difference between how much the current assets return differs from the average return rates. And then on a term which depends on risk, this is the risk, how much the current assets risk is different from the average risk in the market, and this term here. What is interesting is that the R term here is a term which characterizes the market. In a bull market, in a booming economy, R is going to be large and positive. In a recession economy, R is going to be negative. And so it shows that depending on how much the economy is doing, the financial economy is doing, then you have an allocation which depends more or less on returns. In boom economy, returns are very important, and so they don't much look at risk. In a recession economy, with this model, returns are less important, and there's a flight to quality, a flight to liquidity. So that's already a first interesting insight that we get from the model. The second thing is, and I'll be brief on that, is how much can we say about the capital adequacy ratio? And so the literature goes on, if you increase the capital adequacy ratio, then there's going to be an increase in lending rates because banks have to fund more equity, either by returning earnings or because they have to sell more equity. But in any case, they want to defend the return on equity, and so they need to raise the interest rate. And so there's a vast literature on that, and it looks at how much the lending rate increases and how much there's a decrease in credit volume and then the impact on the GDP. Of course, if we were in the Molyneux-Miller world, that shouldn't happen, but we know there's plenty of reasons why Molyneux-Miller doesn't work. I won't go too much into that. What we do know is what we can do is look, okay, what if we take a derivative of the QI expression we just got with respect to CAR, and is there a case where without changing the return rate, we can still have delta QI over delta CAR equal to 0? Meaning, the bank does not have to change its return to make sure that its Q doesn't change, because banks are interested about not changing their Q, so can we be? And yes, it can be the case. Of course, the risk is supposed to decrease, but and the wage, the share equilibrium should increase, but the R term here, again, the fact that the market can be in a bull state or a bear state will impact whether bank will have to react or not. And what we show here in this model is that if we are in a booming phase, and if the CAR increase, i.e. procyclical CAR, banks will have to react. They are more likely to react than in a recession case. Meaning that there's no need, meaning that the literature which have been seen where we have this increase in lending rate and decrease in volume rate, volume lending will be impacted by the Q. This also could be related to Minsky's idea where the tipping point is a change in the interest rate. You can either have it by the bank, the central bank raising interest rates. Actually having a procyclical CAR could also be the triggering point where banks react by having the higher CAR and hence increasing the lending rate and hence starting the downfall of Minsky's bubble. Right, so what have we shown? Well, first of all, Practically, the fact that we can reduce the way in which the lambda I zeros and lambda ij's are computed simplifies the usage of a Topping's equation. We can easily extend the model for more assets. Theoretically, we basically specify explicitly the implication of risk on a Topping's portfolio asset, and we highlighted the importance of flight to liquidity in the specific case of the car. And as I said, we want to go further into the car analysis and then try to see what happens when QE targets specific assets. Do they buy bonds from government? Do they buy bonds for banks? And how is this going to have an impact on the bank's reaction to it? And of course, we'd like to go on to the empirical estimation of the model we propose. That's pretty much it.